Welcome, and we're very happy and excited to be here today and to present to you our talk, Dashboards and Dragons, Crafting SLOs to Tame the AI Platform Chaos at Scale. So welcome, brave adventurers, to our quest where we'll craft the SLOs to vanquish the chaos haunting our AI realms. My name is Alexa Griffith, and I am a senior software engineer at Bloomberg. I work on building our AI inference platform.
My name is Ankita, and I'm a senior product manager at Bloomberg. I focus mostly on our compute infrastructure.
Nice. So our quest begins. As you can tell, I had a little bit of fun making these doodles for this presentation. So let's check out our treasure map for today's journey. We're going to tackle the GenAI Hydra, peer into the crystal ball of observability, and then venture deep into the dashboard dungeon and defend against the fortress of platform challenges. First, a little bit about AI platforms at Bloomberg. We service the whole model development lifecycle. So from exploration with the data to building your model and experimentation to deployment, serving, and then model maintenance and production for monitoring and updating. So what this looks like is various platform teams and services within AI platforms. So we offer services like Jupyter Notebooks, different ways to train and use HPC, managed serving, managed inference, and different AI pipelines and tools to our users. So let's get into SLOs. Think of SLOs as ancient runes, each holding the magic to illuminate the health of your platform. So decoding these runes can give us clarity in uncertain times. So what makes up an SLO? First, a service level indicator, SLI. This is a metric generated by a query. So an example is latency, throughput, or error rates, what you want to measure. Then you have an objective. So that's the desired performance for that SLI. So if it's latency, we want our latency to be under 50 milliseconds, for example. Next, we'll have a target value. So how often must this objective be met? So 99.999% of the time, for example. Next, how do we measure it? With a time window. So that's the duration over which the target value is measured, for example, over a 2-hour window, over the last 24 hours. So just like any magic potion, SLOs combine carefully chosen ingredients. So what we need is a common language between our engineers, operations, and stakeholders. We want it to be user-focused, so we want to highlight real impact and let it allow us to prioritize improvements. Next, we use these for guidance. So this helps us to clearly navigate trade-offs in reliability, innovation, and velocity. So there's different quests, different platforms, different quests, right? Not every quest has the same dangers. Similarly, not every platform has the same needs. They all face different challenges and different things they need. Some things can be similar, right? There are a lot of similarities we want all of our quests going through, but there might be specific needs for specific platforms. For example, training and predictive inference and GenAI. Today we're going to focus on GenAI because that's what we've been working the most on. So for GenAI, our usage patterns could be, real-time inference. We might have interactive workloads. We might have some batch things going on. Also, what we care about is, managing how many tokens we're getting in, the concurrency, the streaming latency, and the availability. So the GenAI Hydra is tricky. You chop off one head, like inconsistent deployments, and 2 more heads pop up, like security or observability issues. So we should arm ourselves wisely. What makes these platforms complex? Well, there are multiple things, right? Like fractured networking. So we have latency, service discovery, cross-cluster traffic. A lot of times now we're running on a hybrid environment. So observability between, something like Amazon, AWS, Bedrock, and running things on-prem. And we have different deployments, like different infrastructure, versions, and scaling. So all of these things make it a little bit difficult to manage. So for an overview, let's look at what a typical GenAI platform will look like from a high level. So we might have a load balancer. We might hit a gateway for us. We use the Envoy AI gateway. And we use that to be able to serve on-prem, a managed inference Kubernetes cluster. And we use Kserve with that. But also, we use it to easily be able to hit any other LLM provider that you need. So this is what a request going through our platform would hit. Now let's follow the request request. This is just an example. Say we have a request, it's going to hit the gateway. It might need to go through some hops in the gateway as well. Maybe it has some authorization things to do. Maybe it has the rate limiter set up. And then once all that is configured, it'll go back to the gateway. And then it'll go to the model provider. And let's say that we're running something self-hosted. Well, then we can also manage doing inference, and it might have to do a prefill, decode, and then hit the inference, and then all the way back, again, the response goes to the client. So at each step, there can be latencies. At each step, there can be failures. And we need to, as a platform team, clearly understand and manage what is going on at every one of these. So measuring our GenAI success. We have client-facing SLOs that determine our quality of service. So these are crucial for our SLAs. So these metrics define user experience and ensure that our platform delivers on promised reliability, latency, and performance. And we have different levels. So for a platform, you might want to have a high priority level. So user-facing real-time, medium, maybe that's like internal real-time, and then low. So our batch inference that doesn't need to run on a specific time. Then we have, to help us with these, we have platform-level metrics. So we track our infrastructure health at each environment. And then we also have use these to guide our scaling and resource planning. Lastly, we have model-level metrics which help us. So we want to know the performance of the models, self-hosted or vendor. And then we want to use certain metrics for determining the reliability, latency, and cost efficiency of our platform. Let's talk about that, our spell book of metrics. So for example, a GenAI platform might want some things for reliability, uptime, including the routing layer, API conversion errors, cost effectiveness, things like how well are we doing for optimizations like automatic routing, model caching, prompt optimizations. Also, we want to measure our scalability. Not only do we want to know the number of requests, but for GenAI, we want to know something like the number of tokens or time to first token. Also, we want to clearly measure our latencies. So from every platform component and the request that I showed earlier. So imagine that as platform teams, so we're in a unique position, right? We're not just responsible for monitoring our service or a few services, but the overall health of the platform itself. So imagine a scenario as a platform team. You have resources across your platform. You have users' resources, infrastructure resources, and all of a sudden they're wiped out. Was it a scheduled cleanup job? Like how much was wiped out? Was it something that was misconfigured, that ran wrong? Was it a failure in the underlying infrastructure? Or even let's take something maybe a little bit more subtle. So what if latency slowly creeps up across services? What if traffic goes completely quiet? Then the question becomes, how long would it take us as a platform team to notice? In too many cases, platform teams can find out when the users complain, which is, by that point, often too late. So the impacts happen, and the frustration from the users already set in. You're losing trust from your users as well. So without this clearly defined real-time visibility, platform teams are kind of stuck in this reactive mode. But with the right observability tools in place, we can detect anomalies earlier, respond effectively, and most importantly, we can better contain the blast radius before it spreads. So this is what modern platform observability is really about, not just dashboards and alert, but giving teams the power to stay ahead of problems and maintain confidence in the health of your systems. So without our SLO dashboards, we wandered in the darkness. But now, our dashboards will illuminate our path clearly.
Thank you, Alexa. A little disclaimer before we go into the next part of the presentation. The dashboards that you see here are just for the purpose of demo. They do not represent the health of any application or service in any organization. A common question a lot of us face, even with the best intentions, dashboards often fail. So why do they fail, though? First of all, there's too much noise and very little signal. Take the example here. We are tracking latencies across 9 different models, but with too many things layered in, we cannot really tell what's wrong. There's no connection to any upstream issues or any downstream impact. Second, these dashboards are rarely maintained. As they say, dashboarding is done in the set and forget mode. They get set up once, but as your platform, your infrastructure, your application evolve, they quickly become stale. This leads to misleading signals and even outdated metrics. Third, we run into siloed views. You can see that model 2 here seems to have high latency, but again, there's no connection with the upstream traffic patterns or any downstream impact, or business impact for that matter. And finally, observability without any kind of alerts is just pure storage. Without defined thresholds or SLO-based alerting, teams cannot discern which issues to act on and when to act on. Quoting one of our in-house observability SME, Salfarino here, if your dashboard takes more than 90 seconds to understand, it's bad. And let's just acknowledge, SLOs are hard to get right. So where do you start? Step 1 is to start with user. What does good look like to them? If you're running a backend job, you need not need like a 5.9 uptime for your service. It's well within acceptable latency. So one size fit all will not work here. Next, choose metrics that actually map to the experience, like latency, error rates, throughput. But be careful, just because you can measure something does not mean it's valuable. Pick the ones that actually align with the performance outcomes. Then make sure your infrastructure is instrumented with these metrics. If you cannot reliably collect the data, you're missing visibility into some of these layers. Then test your assumptions. What does that mean? You use some real-world baseline data. In case of existing services, it's always good to look backwards to look forward. Use that data to validate your chosen SLIs and reflect and whether they actually reflect the end-user experience. And finally, benchmark what's realistically achievable. You don't want to aim for 100% if your systems has never even hit like 99.5% uptime. Your SLOs should stretch your teams, but it should also remain attainable. Now, what are some principles of good or great dashboards? When designing effective observability dashboards, it starts with at-a-glance clarity. The goal is to instantly answer, is everything healthy? If not, where should we look first? Simplicity here is the power. We need to design our dashboards with high cardinality in mind. Today's systems generate data with many, many dimensions. Dashboards should be capable of slicing and dicing into those complexities without becoming overwhelming. It's important to balance your aggregated global view with a drill-down capability. You want a top-level pulse of your application or your platform, but also the flexibility to zoom in, whether it's into specific services, error patterns, or time ranges when an issue arises. Dashboards are even more powerful when you supplement them with contextual data, such as traces, logs. It's not just about the metrics, but the story behind them, right? What happened, where, and why. And finally, the focus should always be on actionable insights. It's not enough to just surface the data. We want to drive decisions. Prioritize clear thresholds and meaningful alerts that will help the teams to know when to act and what to act on. Let's look at an example of a typical dashboard for an LLM application. It's well structured into key performance areas, such as success rates, burn rates, error budgets, latency, and throughput. This dashboard gives us a 360-degree view of Module 1's performance with respect to its SLOs over a period of 48 hours. Starting with the good news, the model seems to have perfect success rate even for the past 7 days. That means short-term reliability is strong. However, if we take a look at the 28-day window, we've hit the success rate of 99.9%, which is still at the edge. The burn rate, though, we have exceeded it in our long-term goal. What that means is the burn, and combine that with the burn rate over time chart, right? It's not a spike, but a steady climb. That tells us this is not a one-time outage. It's a pattern of small repeated failures. Looking at latency, we see a lot of fluctuation between time to first token and even the inter-token latency. There are some spikes in both. This could easily be a sign of scaling inefficiencies or model bottlenecks under load. And lastly, while the throughput is relatively low, there are some error bars present. This means no major concern right now, but they could be contributing to your budget burn. Overall, the model is performing well in the short term, but we have seen signs of early degradation, and it's a good candidate for preventative optimization, whether that's fine-tuning your retry logic, or latency tuning, or even adjusting how we handle edge cases. Now we'll break down the previous dashboard into smaller components and just zoom in into what each one of them has to offer. A quick glance here tells me that are we meeting our SLOs? Is there any ongoing issue? This particular view or panel gives me a clear temporal granularity because it summarizes success rates over different period of time. And then it's also supplemented by a time series insight. There's a trend that I can look at, and you can see there's a clear drop on one of the days. It makes it easier to correlate with incident timelines and deployments. Speaking of burn rate, this is a side-by-side comparison of why burn rate is such a powerful SLO signal, especially when stacked across multiple time windows. On the left, we are looking at a transient incident. There's a sharp spike in the 1 hour burn rate, which signals something seriously went wrong. But it resolved quickly, and the longer-term window stayed flat. This suggests there's no long-term impact to reliability. However, on the right side, the burn rate starts low and gradually increases across 1 day and then continues to increase across 28 days time window. This is a classical pertinent issue. Nothing looks critical at the moment, but over time, the system is quickly eroding the error budget. And this slow burn rate often slips into the radar if not monitored. Monitoring multiple windows helps distinguish a noisy blip from a real structural reliability issue. Both scenarios result in different kind of risk. One is a fire drill, and the other one is a slow drift in SLO violation. You need different responses for each. Now, before we move on to the next dashboard, let's take a minute to understand a few critical concepts of latencies in a typical LLM inference. Time to first token, which is TTFT, and inter-token latency, ITL. Time to first token is the time it takes from when a prompt or an input is provided to a model to when it returns the first token. It's absolutely critical for perceived responsiveness. As fast time to first token gives user confidence that the system is working. And in conversational interfaces, it defines the first impression. Inter-token latency is the time taken to generate each subsequent token after the first token. From the user's perspective, this governs how responsive or smooth the output is streamed, especially for longer use cases such as documents, code, and summaries. If ITL is consistently slow or inconsistent, the user experience is jerky and delayed, even if the first token comes back quickly. Now, taking those two metrics onto our dashboard, this focuses on streaming latency for one of the models. And as we can see, TTFT hovers between 400 to 700 milliseconds, which is reasonable for a production-grade inference service. But there are some dips and spikes. This could be linked to cold starts, load imbalance, or even back-end queuing, even before the inference actually starts. ITL is mostly low and consistent, but there are periodic spikes, even up to 1400 milliseconds, which could indicate concurrency limits, batching inefficiencies, or even degraded transformer performance. Together, these two metrics offer us a holistic view of user-perceived performance of a LLM application, and we want them to be low and stable. This kind of observability is not only essential for engineers, SREs, or platform owners, but also for product teams, because when it comes to Gen AI, performance is the experience. Again, this is a very simplistic panel for throughput. Out of the total requests, every single one returned 200 OK, which on the surface signals excellent performance and no user-facing failure. We see 0 400s, meaning no client-side misuses like bad input or malformed request, Also 0503s, suggesting no infrastructure issues, model timeouts, or overload errors. Now, while this might seem perfect on the surface, in most production environment, a true 100% success rate is often alarming. So this is a quick prompt for us to check. Are we correctly capturing error responses? Are failures being retried or overwritten before reaching the metrics? Are we filtering out any endpoints or failure types? If everything checks out, this gives us strong confidence that the system is performing reliably. But if not, we might need to revisit our instrumentation to ensure we are seeing the full picture. Talking of a different kind of throughput, which is more relevant for an LLM application, token throughput, broken into prompts and generations. First, we see there's a large spike in prompt traffic early on. That could indicate it's a bad job, a burst of inference load, or high demand from upstream service. Following that, we observe continued bursts throughout the day with our gateway traffic gradually tapering off. And right after, the activity completely drops off. This could mean a scheduled shutdown, a traffic routing issue, or even a scaling event. Another key insight, generation tokens consistently stay low, even during periods of high prompting. That could point to very short completions, or prompt-only operations such as embeddings or validations, or possible inference failures or timeout post-prompt. This kind of throughput analysis is important because it helps us correlate our usage pattern with cost, error budget, latency. Next, we have a dashboard which monitors the end-to-end performance of an inference service. It gives us detailed look into the response time across the predictor stack, from the gateway to the queue proxy to the model itself. On the left, we see percentile breakdowns of latency. And the good news is P50 is under sub-millisecond. This is a strong indicator that their network and routing layers are healthy. However, when we shift to the actual model inference, you'll notice that the response times are higher. That's not alarming, but it actually tells us bulk of our latency lies within the inference and queuing. Looking at the middle in the right panel, queuing delays show some spiky behavior. This suggests that there's some intermittent queuing pressure, likely due to bursty load patterns or even uneven request patching. While these spikes do not appear to degrade overall performance significantly, our trail latencies remain within acceptable limits. Overall, the system is performing well, but these traceable queuing spikes highlights areas for possible optimization. And finally, all response code latencies are tied to 200 responses, which means we are not seeing any latency inflation due to retries or errors. And that's exactly what we want. Moving on to a different type of dashboard, which I tend to use pretty much every day, which is utilization of your infrastructure. This gives you a focused view of GPU resource demand and usage over a 7-day window. Specifically for a cluster that I'm looking at, it combines real-time and historical context to assess how effectively GPU resources are being requested and utilized. As you can see, there's low and sporadic usage through most of the week. Even when the requests were high, actual utilization remained well below 100%. I would say even below 40% for some. This indicates a potential gap between allocated versus used resources. The system may be suffering from inefficient job scheduling, over-provisioning, or idle allocations, signaling optimization opportunity either at the workload or scheduling level. Now, talking about supplementing your dashboards with contextual data, this is an example of a distributed trace for an inference call. While all operations are within a single service, it spans multiple internal steps. What you notice here is inference request actually takes up majority of the time, signaling this is the main bottleneck. Supporting spans for model selection, input validation, or even HTTP response sending are comparatively lightweight. You'll notice that there's a few preliminary operations like validation, model selection, and they are lightweight, right? So if we look deeper, though, this trace is not just useful for debugging slow requests, but for understanding where to invest optimization effort, whether that's reducing model latency, caching results, or even parallelizing tasks. Now that we have defined SLIs and SLOs, the next step is to make them actionable. And that's where burn rate-based alerting comes into picture. A burn rate tells you how quickly you're consuming your error budget. When the burn rate is high, it's a sign that the system is degrading faster than our SLO allows. Let's break it down, right? With some examples here. A 1-hour burn rate above 13.5 means your system is burning the entire error budget for a 30-day period in 2-hour window. This is likely a major outage, and you want a high priority alert here. A 1-day burn rate over 2.8 still isn't great, but it could mean a moderate issue, and that's not immediately catastrophic, but could escalate fast. And if your 7-day or 1-day burn rate exceeds 1, you're seeing a slow burn. Less urgent, but it might be a sign of ongoing degradation or even user-impacted behavior. The key is to match these thresholds to your environment. Don't treat your dev and prod the same. You want to surface high severity issues in production faster, but not drown in noise elsewhere. Also, don't just fire alert for any blip. Focus on meaningful, sustained violations and prioritize based on severity and impact. And finally, remember, alerting is not static. You'll need to tune it over time. Use data from your incident reports, postmortems, and SLO reviews to refine your thresholds and logic. Taking the learnings from how you can fine-tune your dashboards, this is an example of what we can call a persistent failure mode. This could likely be due to a misbehaving deployment, an upstream dependency failing intermittently, or poor handling of edge cases causing request failures. Because burn rate remains high across all the windows, this isn't just a spike. It suggests that the issue has been ongoing and not fully mitigated. At 10.3, the platform is burning through the entire allowable budget 10 times faster than tolerated. This is actually critical and unsustainable. Observe scattered dips and in success rate here during the burn window. These dips actually correlate with the periods of elevated errors. And the errors are frequent and sustained rather than isolated anomalies. Then there's this example, just 100% straight, 0 burn rate throughout all the time windows. Looks too good to be true, right? But it actually suggests either the metrics aren't being collected accurately, errors are being swallowed or misclassified, or there's a discrepancy in how we have defined success or failure for this particular service. In a production system, especially one handling real-world traffic, this level of perfection across all time windows is highly suspicious and should be prompting a deeper review. So how do you fine-tune your SLOs, right? You start by grounding in reality. You looked at the patterns of how your error budget is being consumed. If you're not using it at all, your SLO might be too lenient. On the flip side, if you're burning through your error budget consistently, the target might be too aggressive or misaligned. Patterns in burn rate can actually tell you what a common type of error is, whether it's and which part of the workload it is. Every incident is actually a learning opportunity. If you had downtime that did not register as a violation, that's a sign that your metrics or thresholds might not be measuring the right thing. To wrap things up, if you're building or running an AI platform, observability isn't optional, it's foundational. We have seen how robust observability stack built with open source tools such as OpenTelemetry, Prometheus, Envoy give you full visibility across inference pipelines, networking layers, and the GPU resource usage. But tooling alone is not enough. Best practices matter. This means correlating your logs and your traces to shorten your mean time to resolution. It also means setting smart, achievable SLOs and automating alerts based on burn rates and not just vanity metrics. And most importantly, observability is never done. The most resilient platforms are the ones where feedback from incidents, data, and your users constantly feed a loop into refinement and improvement. If you walk away with one idea from today, treat observability as a product and not just a tool set. Build it as you evolve your platform and how it grows. Just a small plug-in, we're also hiring across multiple roles within our AI org at Bloomberg. Thank you.
That was it.